Here are two questions. How big is the Eiffel Tower? And what is the height of the Eiffel Tower? Anyone reading those understands immediately that they are the same question. Now look at the actual words. They share the word the, they share Eiffel, and they share tower, and that is it. Big and height have no letters in common. Nothing in those two sentences, taken purely as text, says they are asking the same thing. For most of the Internet's life, search worked by matching words. You typed something, the engine looked for pages containing those words, and it ranked what it found. That works remarkably well when you happen to use the same words as the page you are looking for, and it fails completely when you do not. Ask for something big on a page that says tall, and the overlap is not weak. It is 0. Those two documents have nothing in common that a word index can see. This is the math behind. Today, how a computer knows that two sentences mean the same thing. So here is the question this video answers. What would it take for a machine to see that those two sentences are close? Not to understand them the way you do, just to put a number on how close they are, and to get that number right often enough to be useful. The answer turns out to be a piece of geometry you already know. Start small. Forget the whole language and pick 6 words. Big, height, tall, Eiffel, tower, museum. Now any sentence can be written as 6 numbers. How many times each of those words appears in it. How big is the Eiffel Tower becomes 1, 0, 0, 1, 1, 0. It has big, it has Eiffel, it has tower, and it has none of the others. The sentence is now a list of numbers. Nothing has been understood. It has just been written down differently. Do the same to the other two. What is the height of the Eiffel Tower becomes 0, 1, 0, 1, 1, 0. What time does the museum close becomes 0, 0, 0, 0, 0, 1. 3 sentences, 3 lists. And here is the move that changes everything. A list of 6 numbers is a point in 6-dimensional space, which means these sentences are now places, and places can be near each other. 6 dimensions is hard to draw, so take 3 of them. Eiffel, tower, and museum. The first 2 sentences both sit out here, in the corner where Eiffel and tower are both 1. The museum sentence sits over there, alone on its own axis. You can already see the answer with your eyes. What we need now is arithmetic that agrees with them. The tool is the dot product, and it is the simplest thing in this video. Take 2 lists, multiply the first number by the first number, the second by the second, all the way down, then add up everything you got. That is the whole operation. 1 multiplication per slot, and then a sum. It is the first thing anyone learns about vectors, and it is doing all of the work here. Run it on the first 2 sentences. Big, 1 times 0 is 0, height 0 times 1 is 0, tall 0, Eiffel 1 times 1 is 1, tower 1 times 1 is 1, museum 0. Add them up and you get 2. Now run exactly the same thing on the Eiffel sentence and the museum sentence. Every single product is 0, because wherever one of them has a word, the other does not. The total is 0. Not small. Exactly 0. Here is why that number means anything at all. There is an identity connecting the dot product to geometry, and it deserves to be on screen properly. A dot B equals the length of A times the length of B times the cosine of the angle between them. The left-hand side is arithmetic. Multiply and add. The right-hand side is a picture. 2 arrows and the angle between them. They are the same quantity. That identity is the bridge this entire field is built on. But there is a problem with using the dot product directly. Take the first sentence and simply say it twice. Every count doubles. The whole list doubles. And when you run the dot product, the answer doubles as well from 2 to 4. The sentence did not become more similar to anything. It just got longer. A measure that rewards length is not measuring meaning. It is measuring size. So divide the size out. Take the dot product and divide it by the length of the first vector and the length of the second. Then look back at the identity and watch what survives. The lengths cancel on both sides. What is left is the cosine of the angle, and nothing else at all. That is cosine similarity. It is the dot product with the size removed, and the only thing it can still see is direction. You might reasonably ask why we use the angle at all, rather than the straight line distance between the 2 points. Here is why. Take a short news article and a long one, both about exactly the same event. The long one uses every word more often, so its point sits much further out from the origin. By straight line distance, those two documents are far apart. By angle, they are almost identical because they point the same way. Distance measures how much was written. Angle measures what it was about. Now the actual numbers. Our two Eiffel sentences, dot product 2, and both lengths are the square root of 3. So the cosine is 2/3, 0.6667. As an angle, that is 48.2 degrees. Not identical, but pointing broadly the same way. The Eiffel sentence against the museum sentence, cosine 0, 90 degrees, perpendicular. In this space, having nothing in common is a right angle. None of this is new. Comparing documents by the angle between them was published in 1975 by Gerard Salton at Cornell. This geometry is over 50 years old. Now the part where I have to take the toy away. Real systems do not count words. Counting words would tell you that not good and very good are nearly identical, because they share almost all of their text. Instead, the numbers are learned. A model is trained on an enormous quantity of text with a single goal. Arrange things so that pieces of text used in similar ways end up pointing in similar directions. Nobody picks the 6 words. Nobody picks any of the numbers. They fall out of the training. And there are not 6 of them. One common size is 1,536 numbers for a single piece of text, not 6 words. 1,536 coordinates, not one of which has a name you could say out loud. Comparing 2 sentences means 1,536 multiplications, and then adding them all up. The same operation you just did by hand. There is one more trick, and it is the reason this is fast enough to be worth doing. Notice that dividing by the length is something you can do once, in advance. Scale every vector so that its length is exactly 1, and store it that way. Then the division has already happened, and cosine similarity collapses back into being just the dot product. Multiply, add, done. No square roots at all when the question arrives. You cannot picture that space. Nobody can. But notice that the formula never asked you to. Multiply the matching slots, add them up, divide by the 2 lengths. There is nothing anywhere in that recipe that cares whether there are 3 slots or 1,500. The geometry keeps working long after the picture stops. And here is the part that almost nobody explains. Why does having a huge space help rather than hurt? Take 2 completely random directions in 3 dimensions and measure the cosine between them. On average, you get about 0.5. Random things look fairly similar, purely by accident. Now do the same in 1,536 dimensions. The average falls to about 0.02. In a space that big, 2 random directions are almost exactly perpendicular. So when 2 real sentences score 0.8, that is not a mild hint. In 3 dimensions, it would be close to meaningless. In 1,500, it is an enormous coincidence, unless the 2 things are genuinely related. And that is the whole machine. When you search or when a chatbot looks something up before it answers you, your question is turned into one of these vectors. Every document it can reach has already been turned into one, in advance. Then it computes the cosine between your question and the candidates, and hands back the closest ones. That is all. There is no understanding anywhere in that loop. There are only angles. Which is also why it fails in a very particular way. I loved this film, and I hated this film score extremely high together. They are the same sentence apart from one word, and that word turns up in almost identical contexts during training, so it lands in almost the same direction. Negation in general is a weak point. Cosine similarity does not measure meaning. It measures closeness in a space that was arranged so that similar meanings usually land nearby. Usually is doing a great deal of work in that sentence. So, a machine knows that two sentences mean the same thing by turning each of them into a list of numbers and measuring the angle between them. The measuring is the dot product, divided by the lengths. It is the same formula you would use to find the angle between two arrows drawn on paper, running in a room with 1,500 dimensions instead of 2. The room is new. The geometry is not. Thank you for watching, subscribe, and see you in our next video.